prediction is one side of the story, which is, for them, is just an excuse to go in and look in a more interesting way. And typically, what they really care about is understanding. So they want to understand how things are related to get. So one test is not enough. The problem is complicated, so you need another entry point to get a good model of what's going on. So the simplest example could be, for example, when you have expression data, for example, gene expression data, and say you have the example I made the first day. So you have a patient of type A and type B, okay? And what happens is that, in principle, you could say, well, I really want to make this machine that when the patients arrive, I'm just going to measure the expression level, and then I'm going to say if it's type A or type B, and then I might need to use these kind of drugs or these others, right? That's kind of a dream. If you, I sometimes share this epiphany I had at some point when I was looking, in the brief time of my life when I was looking at this kind of data. If you go in and look, I don't know about you, but for me, when I see the name of a disease, I think that it's a very clear status. Okay, like if you have whatever disease, it's a very well-defined status, and you're all the same. And it's actually not true. If you go in and check, basically they see that there is a distribution, more or less you have this and that, but each of us ends up being, to some sense, sick in a different way. Okay, and there is a lot of variability, and sometimes it gets to the point that it's very hard to cure because the variability inside is so big. Sometimes you cannot even name it. Okay, I don't know. I think people here are still working on arthritis for kids. For adults, there are some measurements that clearly distinguish the different kind of arthritis you can have. For kids, we don't have it. There is, because we haven't understood it yet, okay? And this is problematic because you don't know how to cure it. You don't know how to recognize, say, the aggressive one or the degenerative one or so on and so forth, okay? So whenever we speak about the disease, in fact, it's this kind of blurred concept. And the dream would be to be able to just do targeted medicaments, okay? So the medicine for me, okay? And if we could go to the genetic level and really understand the process of this would be the dream come true kind of stage. We're definitely not there yet. But this all to say that oftentimes when you're in this kind of situation, what you really want to do is not only to make a prediction, but actually to understand better which, for example, genes are important for the prediction. Okay? Because what the doctor does or the clinician does is that you provide him with a list of genes, and then you're going to go in and, for example, measure them in a better way. Because to measure a lot of genes, you end up being pretty rough. So you go in and really measure a bit better, reduce the signal-to-noise ratio, and understand better if that's going on. And then you can cross-reference with all the other information you have about other ways of studying things. You have one study, another study, and then a picture emerges, which is not a statistical model, is a human thought model, which is this combination of these different views and different data. Rob Novak, who's a colleague in Wisconsin, recently was saying that sometimes in this perspective, you can look at machine learning as kind of the tools like a microscope was, or it still is, but to give you other ways to look at data, okay? So you have this way of looking at data, you have this other way of looking at data, you have this other way of looking at it. It's a bunch of tools. It's less of an artificial intelligence perspective, but it's very true. When you have to do data analysis, machine learning is just a bunch of tools. And so in this sense, one idea is, can we use some techniques like the one we've seen to study the data and try to get models that are informative and not only predictive. So we're going to focus on a specific aspect of this, what is called variable selection. And the idea is that we want to go beyond prediction, okay? So we want to do beyond classification or beyond producing the price of the house. We really want to know, how do we do that? What are the kind of information that are important to do this, okay? Now, again, think of a second of the situation with genes, okay? You have a matrix. You have, say, 50 patients, and for each one you measure the gene expression, which is in the order of tens of thousands, okay? Now, suppose you've just listened about PCA for an hour and a half, okay? And you have to remember what I said. Then what you could do is say, you know what I'm going to do? I'm going to take this big matrix, I'm going to project it down to, say, 3, 4, 5 dimensions, and then I'm going to try to make prediction out of those. Sure, what's the problem with this? Nothing. If you want to do prediction, that's perfectly fine. And actually, that's one way of doing things. Of course, you're assuming linear interaction between the variables, right? But why not? But suppose that my question is, don't give me only a good predictor, give me good genes. Okay, what's a gene? Well, if you have this long matrix, the rows are going to be the patients, the columns are going to be the genes, right? So if you do PCA and then you try to do prediction, how can you tell me which genes are important? Well, suppose you're lucky, okay? The first column is the first principal component. If that's the case, you're super lucky, right? Because then you just look at the first principal component. That's the first gene. That's important. You're good. But this is not at all a generic situation. This is very peculiar. In fact, if two genes, two columns, and this happen, are both important, you can have all possible combination of them, and this will give the same PCA. You can write one vector in many, many possible ways, right? So when you look at factors that are important, PCA mix everything together. Okay? The game we want to play is a step up, and it is we want to select. We want to know which columns are important. Okay? Why? Because we are assuming in this game that measurements do matter. They're not just pixels. Okay? They are gene 1, and gene 1 there are diseases, for example, that depends only on 1-2 genes. Okay? So once you figure that out, you can knock them down or try to see how they mutate, and you understand basically how the disease works. And you can make many situations. This is dramatic, but you can say, so, for example, you can think of a situation where what you want to do is build a system which is more parsimonious, okay, in some way. So, for example, the housing price system. You look at all these measurements, and then you figure out that out of 100 of them, 3 really matter. The others don't really matter. And you know that it's the size and whether you have a view. So that's another reason. And you gain a bunch of stuff. You gain interpretability. In this case, you also see that one thing you gain is compression, right? Instead of having to look at all the data and carry them all around, you might go from 50,000 dimensions to 3. So you also do dimensionality reduction. The big difference here is that instead of attaching this, you do two things. A, you attach the idea of dimensionality reduction to prediction. So we are going back to supervised learning, not reconstruction. And two, you raise the bar. You don't want to do only dimensionality reduction, but you want to do variable selection, column selection. Okay? So this is what we want to do next. Make sense? You see the difference with the PCA? PCA looks at reconstruction and then mix everything to give me some direction. And then I have to go in and try to understand which direction were important. We're going to bypass that going back to supervised learning. In fact, one could see that one could even try to extend PCA to use some of the idea I'm presenting here, but the supervised learning setting is the basic one, is much simpler, okay? And this stuff turns out to be probably the piece of applied math and statistics that received the most attention in the last 10 years, and is one of the biggest trends in applied science in general, so this is a good place to start. So is the difference between PCA and what we want to do clear? Wonderful silence. Anybody want to hear it again? Worse than going back to supervised learning, we're going back to linear models. Okay? This is kind of a problem, but you'll see in a minute why linear models do matter still. And also, we're going to just look at that equation, the simple equation of a linear model, just with a slightly different eyes that we didn't say so far, which is kind of obvious. If you have a linear model, you basically have that you can write it as a sum. And then you have a weight for each of the entries of the vector, right? But each of the entries are related to the measurement that we want to select. So if you want, another way to say the problem is, given a vector of whatever number of dimensions, you want to see which indices you should keep. Now, you have one weight per index. So one idea is that perhaps the way we should go after this problem is try to check which weights are important and which one can be essentially discarded, or maybe put to 0. So that's how we're going to do it. So let's complain about this before we embrace it. What's wrong with this? You like it or not? Depends.
Depends on how much information we are discarding.
Of course, yep. So that's for sure. So, of course, if you start to discard, you have to tell me how you're discarding, okay? So that's what we want to do next. What else? I mean, there's a fairly obvious complaint that one can make at this point. So we're going to use prediction as a guiding principle, and we're going to look at linear models. After 2 days of talking about non-parametric models and kernels, that kind of feels a little annoying, no? The reason why we do this is because we're typically going to think of a situation where really the number of measurements is redundant. Okay, we have many more measurements than points. And also because we're going to use this notation, but really you can think of this xj to be not the real x, but actually it's some kind of measurement that we can look at. So the typical example here is, say, in the case of genes, oftentimes you have 100 patients, and then you measure their genes, which I say basically 20,000, 30,000, and so on. Okay? So it's a problem which is over-parameterized. So while there could be nonlinear interaction, it's like you don't have the budget of data to actually appreciate these nonlinear interactions. Okay? That's one way to look at it. This is still annoying because from a modeling perspective, you can think, well, maybe at some point I do get this data. Right? We're going to give up to that for today. The other thing you can think of is, say in the case of images, you don't have to think of those as pixels. You can think of those as the output of a bunch of kind of measurement that you do over the pixels. You can take the pixel to tomography, look local averages, gradients, and so on and so forth. Okay, so they don't have to be the pixel themselves. They can be some other measurements. I use this notation because otherwise we have to write phi, j, x everywhere. Okay, but in your head you can just make this exchange if it's useful. So one question we won't touch upon much is, how about nonlinear variable selection? Okay? Long story short, this is a much less developed field, and there are like 4 papers in the world. So that's actually a good topic to work on, but it's hard. It's hard because we are solving a problem which is much harder than pure prediction. We want to actually understand interaction of the variables, and if the variables start to be few, more than few, being nonlinear, it's hard. So we're going to stick to this for now, okay, and see how far we can go. Do you have other complaints aside the one I raised? Because what we're going to do right now is that we're just going to like this and see what we can, starting from this, how far we can go. All right, so this is what we want to do. This is the model we start with. And the key assumption is that we're going to, you see this word important? We're basically going to translate, we're going to formalize this importance in basically saying the best function that describes my data has a lot of zeros here. If it does, it means that a lot of the variables here can be just thrown away. This is a fake sum. I don't know why this is V, because we call it D until 2 minutes ago. Okay? A lot of those can be discarded. So this V, if you want, is much smaller. It's not the whole set. Okay? If this happens, we say that the solution is sparse. Because most of the entries of the vector describing the solution are 0. And here, I'm thinking of the best possible solution, okay, the target function. Not the one I found today, the one I found on the data. The one I could find with infinity data. If that's sparse, then there is a hope that I can actually try to estimate it by few degrees of freedom. Okay? Yep.
Just to go back a bit, is there another issue with the correlation between the different variables?
Yes, we get to that. So the question is, we haven't introduced the data yet, but in a minute you will see that there is a problem if things are correlated. Okay? You're not disturbing at all. Very discreet. All right. So, why do I have the same slide twice? Am I retarded?
Thank you.
Oh, you're welcome. Oh, okay. I just went back. Oh, I have the same slide twice. Amazing. All right, we need some notation, okay? But more or less we already introduced it. So xn is the data matrix, which is n by d, is the input. Now I also introduced the, well, this is a mistake. It's the columns that I call xj. We're going to use them at some point. I'm going to remember what they are. yn is the output vector, okay? So this is kind of one first place where correlation comes in. I'm not sure how much if we wrote this explicitly, but it's kind of clear. If you have to solve, if you have data and you want to find a linear system, you're basically starting with the, if you have data and you want to find a linear model, fit in the data, you essentially have to find solve the linear system, okay? And this is the linear system. By the way, I'm taking the offset away because you can put it back easily, and I don't want to have the destruction, okay? So I'm not going to put an offset. I'm just going to look at the purely linear model. So back here, so you want to fit the linear model to your data. This means that you have to solve a linear system, okay? And classically, in classical statistics, the idea is the size, the amount of data you need is roughly speaking of the order of the number of variables that you want to estimate. So if D is 100, N has to be order 100, okay? Now, in modern application, this happens quite often that D becomes of order of thousands or tens of thousands or even 100 of tens of thousands. This would mean that every time you need a lot of examples, okay? And here, as before, the saving grace is assuming, so you call this second situation the high dimensional situation, where the number of points is much less potentially than the number of dimensions. And you see that basically this corresponds to a situation where you don't have enough equations for the variables you need to solve. And I always switch this, so I think this should be wrong because the high probability I switch this. Now, how can we do if we don't have enough data? So if you have to solve a linear system where we have too few equations, we get a number of variables. What's the catch? We're just solving an impossible problem, or there is something we can hope for? There is something we can hope for, and we've been doing it for 3 days, in fact. We're hoping that, as we said, even in the case of PCA, our variables are actually not independent with each other. There are things happening, okay? There are things that make our different dimensions related to each other, and the moment we assume smoothness, okay, or even just a constraint on the L2 norm of this, which you can think as a budget on the different measurement, that's exactly what we're doing. You're basically saying, all things are not equally important. Maybe they should be in some subspace, maybe there's some subset, and here we're going to look at a different assumption, which is basically saying, this guy looks big, it's really not, okay? The ideal guy is actually quite empty, and so that's why there's hope. And I even made a wonderful pictures for you. This one I made. This is the matrix, okay? It's short and long. This is the vector. It looks very long. And this is the data, which looks dramatically short, okay? If this is what you have to solve, really, it's hopeless. But suppose that now what you have is that not all the entries are important. The red ones are different from 0. All the rest is actually 0, okay? So you might have, let's say, I don't know, 10, 20, 100 components that are different from 0, and maybe the other 10,000 that are 0. So suppose that I tell you which components are different from 0, okay? I'm God, and I know which components are different from 0, and I don't tell you the value of these weights, but I just tell you which they are, then you're done, okay? If you want to solve the system, if you, for some reason you want to solve this system, you can do it, but it becomes the situation where this matrix is going to have a lot of rows and few columns, the one corresponding to these entries, and the system looks good, okay? I'm back to the classical setting. So here, the question is, how do I discover which entries are important, okay? Because if I can, then I'm back in the game. I need a number of equations which would be proportional not to the true dimension, but only to the relevant dimension, okay? Make sense? So we do take this point of view of variable selection, but this is really as a far-reaching consequences because, where did I write the buzzword? I wrote it somewhere. Yeah, because essentially, imagine, this is not a particularly machine learning-like problems, right? This is fairly universal. This appears in all kinds of inverse problems, compressed sensing, signal processing, all kinds of problems, okay? And so this question had an impact, mostly in signal processing and statistics, where all of a sudden the game is, maybe I can solve problems that I couldn't solve before, because I'm not assuming a worst-case scenario, but assuming an optimistic scenario, where the true dimension is not the full dimension. Okay? And so here are just just a pointer, but really this has been very, very, very big in the last, I don't know, 15 years or so. So, all right, so once we convince ourselves that this could be a good idea, let's see how we can turn it into a procedure we can use in practice, okay? Suppose you have an infinite computer, okay? As much computational power as you want. So don't worry about that side. How would you solve this problem? You have the data, and you want to discover which variables are important. How would you do that?
Trying all the combinations possible.
Of what?
Of non-zero parameters and check which combination gives me the best correlation with what.
Okay, so what you could do, now tell me more specifically how you want to do it. So just expand on what you said a little bit. How do you do it? So you have a matrix, you have this, what do you do?
I will try with just the first number is good, and the first and the second, the third, etc., etc., for infinite.
So basically what you do, another way of saying is, you take one column, okay, and you solve the problem. Then you now take the second column, you solve it, the third column, and you do all the single ones, okay? Then you take the first and the second, okay? This, in fact, essentially turned out to be essentially optimal from a purely statistical point of view. That's a good idea, okay? Then you will have to find out in some way, we're going to discuss in a minute, which one you should take, okay? Because you're just fitting the data, so you have to be careful. But that's basically the best idea, okay? The problem with that is that we don't actually have infinite computers, so this smells like combinatorial a lot, because you have to take all possible combinations. If you look at the number of combinations, first of all, you have to solve a linear system each time, and the number of linear systems you have to grow larger, and it's a combinatorial number. So this is hopeless, okay? I'm going to rewrite this absurd method first, and then we're going to find a way to solve it, okay? So, yep.
Exactly the same that we talked before the break about the decomposition. So,
No.
I mean, you can take the eigenvalue and have
But the eigenvalue are just of this matrix, right? So what I want to do is that so I'm not sure even how you would want to do it. Tell me how you would want to do it. So you take this matrix, you find the eigenvalues and eigenvector, then?
Okay, and then you have the decomposition of the matrix, maybe you have an SDG, and that way you know which column, what kind of, let's say, variance represent of your original data, and you multiply each column by a weight. In order to, let's say, have a sparse reconstruction of your.
Well, how the hell you do that? So yes, you can take this matrix and you can reduce in dimensionality. So instead of n by d, you can take n by k, where k is the number of eigenvectors. Okay. If you do that, at that point, this vector becomes k-dimensional. Okay. It's smaller, but how do you solve the problem anyway? You still have to check k possible cases, first of all. And this may still be very big. And anyways, those new coordinates are not the original one, are the one after you applied the projection. So if you want to go back, even assuming that k is small enough that you can solve a combinatorially hard problem, you still have to go back to the original coordinates, which is going to be mixing. You just have this, this coefficient, the way you mix them all. And you still won't be able to select the original variables. So even if you could solve it, you would be extracting, in some sense, the coordinate in the PCA space. And when you go back to the original space, you mix everything. Okay? So we want to keep this. So what the approach we want to take now is, let's take a regularization approach. Let's try to write the fitting term. Let's just think of the regularization term, and then let's try to see if we can solve it. Okay? And the basic object is going to be this norm, and I'm not going to really explain many things about it, but the definition is easy to see, and it's basically saying if you give me a vector, okay, I'm just going to count how many coefficients are different from 0. All right? I'm not going to give you how big they are. I'm just going to say how many are different from 0. This is not a norm, but it's called the L0 norm. Okay? And what I want to do now is I'm going to stick to least squares, mostly for simplicity. And then this is what you can look at. Okay? Now, essentially what you can check is that by fixing lambda, you're fixing, here you see it kind of implicitly, but you can show it in practice more explicitly, that you're fixing how many variables you want different from 0. Okay? It's the number of variables that you want different from 0. And so here you have a fitting, not smoothness, but a fitting sparsity trade-off. If you keep lambda 0, you're just fitting your data. If you keep lambda very big, you set all the coefficients different from 0. And here you're playing this game where basically we try to cross-validate this parameter to check what is the best number of variables to get good generalization. Not only to solve this, which was basically the linear system of before, but actually to be good on new data, okay, produced by the same source that produced the data you have today. Okay? So the good news is that by doing this, we're going in the direction of regularization. So a lot of the cells in our brain that we activated in the last couple of days can be, used. Okay, cross-validating this, fitting trade-off, bias variance. Yeah, that story. Okay, exactly that one. Only here, instead of smoothness or neighborhood, blah, blah, we're going to think about sparsity in a linear model. Number of coefficients different from 0. Okay? I said it. Now, bad news. Solving this problem is essentially equivalent to trying all possible things, which I kind of call the brute force approach. Okay? So the case where you actually, what you do, so it turns out that this problem is as hard as taking the single variable, the couple of variables, the triplets of variables, so it's not computationally feasible. Okay? So while information theoretically would be kind of the thing to do, but you're done. You cannot do it. So in practice, what people do is they've considered two big ways of solving these questions. Both of them are approximate, but interestingly enough, under certain assumption, it can be shown the problem exactly. Okay? So I'm mostly going to look at them as approximations. So the problem cannot be solved. I'm just going to use an approximation. In fact, while for a generic problem, you cannot say anything, for certain classes of problems, you can actually show that these approximations are tight. Okay? And they actually solve the original problem. We'll get to that. So let me first explain the approximations. I mostly want to spend time on so-called greedy methods because they're easier and they require a little less computation. And then I'll describe convex relaxation. Okay? Yes?
Can I ask a question?
Yes.
It's something conceptual. Because I saw also the other day with the L2 norm,
Yeah.
we were looking for smoothness, which practically resulted into having as many entries as possible, practically close to 0.
Yes.
So although I was thinking, okay, that was also a way to
Yeah.
sparsity and
Yeah. Yeah, this is a very good comment. So so give me a chance to make the comment. So he said, well, we talk about smoothness, but really in the linear case, more than a smoothness is a budget on the coefficients, right? I take a coefficient here, square it, a coefficient there, square it, and then I put a constraint on how big can it be. That's basically what you're doing when you're doing L2 regularization. Now, why do I bother here doing this stuff? Because as he said, if you now look at the coefficients, some of them are small. But they're never, you can actually check that they're actually never, almost never, 0. Okay? So they're practically 0. But then what does it mean practically 0? Suppose that you do what you've done yesterday, okay, or the day before. You solve your linear model, use the L2 norm. Then you get this coefficient vector, and then you check. Okay, you spend quite a bit of time on doing your cross-validation correct for your lambda. And then you get this vector, and then you have to decide what's small. Not clear. How do you do that? Okay. So in some sense, what we want to do now is to start to ask the right question, which is, I would want to make them 0. And then check if there is a way to actually do that, okay, without fumbling with extra parameters. We want to have just one parameter that at the same time sets stuff to 0 and control the fitting simplicity trade-off. Okay? So what you'll see today is that the small difference in the way we define the regularization will make the difference in this respect. So instead of the keyword in what you said is the practically. Instead of practically 0, we're actually going to make it 0. And this will get rid of an extra parameter that will be hard to fix. Okay? This is kind of going to be the whole game here. All right. So before introducing them, you introduce this. Okay, so we don't have an infinite computer. Okay? It's a fact. What can you do? You still want to solve the same question as before. You like to solve this linear system. Ideally, we'll try all possible combinations, but you cannot. So suppose that your life depends on giving me a solution.
Try with random values and then look how the sort of with which kind of prediction minimizes. So instead of using all the combinations, just try out a couple of random ones.
Yeah. But suppose that you have to not only tell me one possibility, but implement it in 10 minutes. What would you start doing? Be slightly more precise. What do you do? So you take some combination. What do you do? You take 3, 4, 5, 1, 50 million. What do you do?
So you sort of start off with a set of specific, like designing randomly, and then you sort of rotate.
Randomly what? Tell me. So we have to do it now. Okay. So I give you a matrix X here. I give you Y. What do you do? And in the meantime, you guys should not just enjoy this, okay? What would you do? Okay? You think about it. Somebody else in the meantime, tell me, what would you do?
So maybe take the most important one.
Yeah.
And then pick the other so that they are different from this one in some sense. And maybe like that when you have the second one, take the third one so that it's different from the one.
So what he says is, check the first best one. That's okay, it's one. You have to still look at all the data, but it's fine. Keep it. Then take it out, okay, and check the second best one. Does it sound like a good idea?
But so that it's not similar to the
Yeah. So you take, I even said you take it out. You can even take it again in, but take it dissimilar. You want to take it maximally dissimilar. Yes, you can also do that. You can also say, I really want it to be, say, orthogonal or something for the first one. Okay? So that's kind of what I wanted to do. You know, the other thing that you might say, because what you're saying is you just start to run, yes, but with 5, with 1, you just took a bunch of 1s, then you look at 2. Well, that's still a lot. So you have to find a way to kind of solve a combinatorially hard problem in some ways. So and the two ways are you start from 1 and you go up. You start from all of them and you shave them down, or something in the middle, but we have to agree what is the something in the middle because I don't even know. We're going to take the first point of view, okay, which is going to be we start with 1 and we keep on going, okay? It's going to be greedy in the sense that we try to go in the right direction and we hopefully find ways to get something reasonable. We have to agree on a few things here, which he said, which are what does it mean to select the best one? What's the best one? How do we compute the solution and how we update it, okay, each time? And we're basically going to check techniques to do exactly this, and we're going to introduce the basic one, which is basically just computing the solution for a single variable, then for another single variable, and just summing up the solution. And the other one that what it basically does is that select one variable, compute the solution, select another variable, recompute the solution for 2, okay, and keep on going. So each time, instead of computing the solution separately for variable 1 and then for variable 2, once you have to update the solution, you recompute it. Okay? One we're going to call it matching pursuit, and the other one we're going to call it orthogonal matching pursuit. So you're basically going to have a notion of residual because the first time you feed the data. But the second time, when you already found a variable, you want to discard it. And so you have a notion of residual, which is what's left. Okay? So you're going to have a residual, the coefficient vector, which is your solution, and an index set, which is the active set of variables that you are selecting. Okay? And you have to initialize them in some way. This is going to be 0, this is going to be empty, and the residual, the first time, is just going to be the output. That's what you want to predict. Then here I don't tell you how, okay? I just give you the list, and now we're going to fill them up with specific equation. So you initialize this object, you pick, here the most correlated with the residual, but correlated here is a quote-unquote, okay? We have to see what we mean by correlation. We say, oh, now in my index set there is this thing here. Then if I already had a coefficient vector, a solution, I have to update it, and then I have to update the residual. And then I keep on going, okay? So you do these steps over and over again. Is the philosophy clear? Now we're going to fill this with specific ways of doing it. So R is going to be the residual, W is going to be the coefficient, and I is going to be the index set, fairly original. And we're going to just start from empty, 0, Y. Make sense? These are the obvious choices. We don't know what's the solution, we just say it's 0. We don't know what's important, we don't take it. At the beginning, we want to explain the whole thing. So how do we pick the most important variable? What we do is essentially solving a least square problem, okay? So we basically say, where is it? Take column J, okay? Just one column. Take the residual at the step before. So at the first round, you have, this is yn. You just take a column, and this is a number, right? So this is a vector of size n, d, 3. How big is this vector? N. The first time is actually yn. How big is this? Well, the matrix is n by d, and this is just a column. So this is n. And so this is just a number, okay? So you solve this, and you get a number for each column, so for each variable. Okay, and the number is this. You plug it back in, and that's the error of that variable. Okay? And you pick the one with the smallest error. If you check that, because you're just dealing with one variable, this is actually equivalent to finding the column which is mostly correlated to the output. Okay? So you just take the inner product, you normalize, and you keep on going. Okay? Here there is some normalization factor going on. This is the first time. The second time you don't have the yn anymore, you will have the residual. So this is the selection step. And as I said, there are these two different interpretations which are equivalent. In one case, we find the best projection, or the data, if you want, this is also giving you the size of the projection. Okay? So in one, you find the best projection or the most correlated columns, or we just find the one which is the column which is the variable which is the best in a least square sense. Same thing. Okay? You're good? Still awake? One shy yes. Then you say, okay, let me put this variable, the one I just selected, let me put it in the set. And you just, you remember vk was the coefficient associated to the variables you selected, okay? So what do? It's a number. You put it, you take, what is this ek? Is the orthonormal basis, so which means that basically it's a vector of all zeros, but the component k where it has a 1. So now you multiply it by these coefficients and you get the vector, which is going to be all zeros, but the k position, which is the one you selected, and there you put your coefficient. Okay? And then you sum this to what you already have. So suppose that, for example, you selected the first coordinate, the first variable. Okay? You compute the solution, and then what you have is that you have a vector of all zeros, but the first component where you have the coefficient you computed. Second round. Let's say, for the sake of simplicity, you select the second variable. You have a coefficient, you fill in a vector with all zeros but the second position, you sum them up, and now you have a vector with the first component different from 0 and the second component different from 0, and all the other ones are 0. And you just keep on going. Okay? The thing which is kind of annoying here is that in this specific instance, you see, this wi is made of components that don't know the existence of each other in a way, but for the presence of the residual. So you don't recompute the coefficient that you already computed. So the coefficient you computed at the first step is never updated, remains the same, okay? Even though later on you take other variables. Maybe that's a bad idea, we'll see. And what you do here is just that given this, you discount this is xn, okay? You discount the corresponding. So this is just the corresponding column. This vector will just, so not the corresponding column, sorry, this is the corresponding prediction, okay? So you just discount it from the one you had before. And then you keep on going, okay? Now you have the residual, now we ended our recursion and we can just start again, and we're basically shaving off explanation of our output by using one variable, two variables, three variables, and so on. Okay? So I think I was lazy enough not to put all this in a single slide, but it's 3 equations, okay? The code is very simple, and that's why I start from this. The matching pursuit, the orthogonal matching pursuit, is the variation where it's all the same, but essentially you want to change this guy and this guy. You change this guy because basically you say, once you give me this set updated, I'm actually going to recompute everything, okay, on the active set. At that point, is that clear? At that point, you also have to change this definition because you're not shaving off the residual that you already have. Each time, you're recomputing everything and shaving it off from the full vector, okay? So instead of just shaving off this from the next one, you redo the whole thing. So the notation here, there are 15 ways of doing it, and I don't know which is the best one. But in some sense, you mask. You just take the full data matrix, you mask it so that you just keep the columns in the active set. You solve, you take the vector, and then you discount it here and get the new residual. That make sense? Of course, this costs more because each time you have to solve a linear system. In the previous case, you just have to solve a one-dimensional problem each time, right? So it's just a linear multiplication. This is going to cost you more, and in fact, turns out that this works better. Okay? This is the algorithm. Yeah. This is that. Yeah. In the sense that it works better in practice, and you can prove stuff for this that you cannot prove for the other. The other one basically can make such big mistakes at the beginning that might not be able to recover later on.
So each time it chooses one new one, which is orthogonal to the previous.
No. So the first step is the same for both. So this one is just the same for both. Okay?
First off, it just chooses the best column.
Yes. But then when you have to compute the solution, you recompute the coefficients on all of them. So the selection step is the same for both. But the update step is different. Okay?
So in what way?
Both. No, and yeah, that was my technical answer. BOH is a very useful Italian word. It means I have no idea. No, I don't know. Be a reason. It's just me that I don't know now, but in 15 minutes I'll tell you. I was lazy enough I was not curious enough to ask this, and I don't know. It may be because the first part something orthogonality happens. I just don't know. Okay, so after this, what do I want to say? I want to say one thing, which is where is the sparsity level? So how do I control how many variables I'm putting in? Well, this is an iterative scheme, right? So it's actually within the iteration. Within the iteration, what I do is basically if I stop, I'm going to have up to a certain number of variables, okay? I notice that in this game, I might actually select the same variable more than once, because I might, get some solution and then take it again, because provided that I have some other new variables, maybe I should put it back in, okay, and just rechange this coefficient. Once now, here, we can have a whole lecture about the theoretical properties of this, but we're not going to discuss them at all. But the long story short is the following. Clearly, we already made the assumption of things being sparse. Okay, that's how we started. That's actually not enough to guarantee that any of this stuff will actually work in practice. What you need to assume is that the columns that are important, okay, are not too correlated. And if you think a second about it, it must be like this. Suppose that you have, say, n points and 100 dimensions. Okay? Sparsity is 2. Only 2 columns are important. And suppose they are perfectly collinear, just for the sake of simplicity. There's no way you find one solution. Any combination of the two will be the same because they're the same vector, right? So I can put, so I have v plus v. Okay? I put 1/2 weight here, 1/2 weight here, and I get v. Okay? And I can put 1 and 0, or 0 and 1. I still get v. I have millions of ways of writing the same vector. Okay? So there is not a single way to write things. And so you won't be able, the problem doesn't even make sense. You cannot go back and get one solution. The problem is not what is called in statistics, not identifiable. You don't have a way to get back to the solution. Okay? So what you need to do to make the math work is assume that the things which are important are not too correlated. Okay? And this assumption has a bunch of fancy names: the restricted null hypothesis assumption, restricted isometry property, restricted eigenvalue. It's all restricted. It's basically, the idea is you are not assuming, so you have a matrix which is, say, 10 by 100 or whatever. It's like this. You're not assuming it to be invertible because that's too much, but you assume that some submatrices are invertible. So if you knew the right column, that matrix should be invertible. That's the idea. Okay? If that's the case, you can actually prove that this kind of algorithm do provide a solution to the original problem. So it's an assumption. The problem was NP-hard. It's still NP-hard. But if you, instead of looking at all possible problem, look at this subset where these matrices are, in some sense, locally invertible, then for those, the problem is not NP-hard anymore, and you can actually show that you can solve it exactly. Okay? I mean, it kind of makes sense, but in fact, the proof is there is a lot of math going on here if you want to make this precise. Yep.
With orthogonal matching pursuit, is that possible that I deselect a variable that I previously selected?
No.
So if you select the first one, it's going to...
Yeah. And this is the basic stuff, okay? So this is what in statistics is called forward stage-wise regression. If you start from all of them and you go back, it's called backward stage-wise regression. Then, of course, what you can do is a forward-backward kind of thing, where you put something, then you take it back, you do some checking. And in the last few years, there have been a lot of variants of this stuff, where you basically try to show that you can improve in some way estimation by mixing the adding and the keeping out, by still making something which is tractable. Other questions? All right, so let's recap 1 second, and then we move to the second, I believe, to the second class of methods. So what have we done here? We ask a new question, which is, I don't want a prediction only. I don't want to do just dimensionality reduction. I want to select which measurements among the one I took to build my inputs are important. And I'm going to use prediction as my guiding principle. Okay, how do I do that? Default method makes sense statistically and information theoretically, but it's unfeasible. So let me try to find some kind of approximate procedure. And the first one is a forward procedure where I select the best, discount it in some way. So select the best, find the solution, discount it in some way, and start over. Okay? And depending on the details of this procedure, you get different techniques. And here we just look at the basic one, and we look at this one because it's simple. Okay? So there is nothing, pretty much. You know, you just have to solve a linear system, or even less, like a one-dimensional regression problem. Now, the other approach requires a bit of convex optimization instead. Okay? So I tend to put it afterwards because, in a sense, the conceptual part is here, and this is one way to solve it. In what I'm going to show now, there's going to be a jump at some point where you would have to take some derivative of something which is not differentiable and do something. And I'm just going to show you the result. And the result makes sense. So we're going to take this route. And the basic idea is that instead of just counting how many coefficients are different from 0. I'm actually going to check how big is their sum. Okay? So this is almost what you've seen on Tuesday, right? What's the difference? There is no square, okay? That's the only difference. So why would this make it, change things dramatically, okay? Why does this make a big difference? As we said, you will see in a minute that this will give you 0. Not practically 0. It will give you 0. And 0, what you put 0, will depend on the same regularization parameter you use to trade off fitting and regularization. Okay? Is that clear? So we go from counting the number of coefficients to summing up their weights, and we go from summing up the square to just summing the absolute values. This is our new problem. Now, there is very good news with respect to the L0 norm and not so good news with respect to the L2 norm. The very good news with respect to the L0 norm, and then one reason for the hardness of the L0 norm is because you can check easily that the L0 norm is not convex in W. It's not a convex functional. So that's essentially one other way to see the source of the complexity of the computational problem. This, the absolute value essentially looks like this, okay? And if you sum it, you basically still have this property. So it is actually convex. The square would look like this. So the good news is that it's convex, while before it was not. What's the bad news? It's not differentiable. There is one point where you have a kink, right? And in that point, you cannot differentiate stuff. But life is good because this is kind of the prototype situation where we know how to use optimization well. So the situation where you have something which is non-differentiable but convex. This is what is called non-smooth optimization. Roughly speaking, well, there are tons of ways of doing it, but roughly speaking, what you need to do is to, well, you have to do many things. Among the things you have to do, you have to extend the notion of derivative to deal with stuff which is not differentiable, okay? And there is a whole branch of analysis called convex analysis that essentially deal with this kind of problem. So this problem has been super popular in the last few years. I guess, of course, people then start to see who's the first person in history that ever wrote it down, and that's kind of hard. I think it goes back to, I believe, the end of the 70s, but I was not up to date with the historical remarks. Roughly speaking, in around 95, in the middle of the 90s, it was rediscovered in statistics called the lasso, which stands for least angle something. I don't know. I don't remember. It's called lasso. Okay? And then in signal processing called basis pursuit. Okay? Which kind of makes sense. You're just kind of trying to pick up a basis. Is somewhat the prototype example of a sparsity-based regularization, okay? Feasible sparsity-based regularization. So, as I said, you cannot just take the derivative and set it equal to 0. You have to do kind of a related idea. And if you could take the derivative and set it equal to 0, you would get something like gradient descent, okay? What you see here is that instead you get something that almost looks like gradient descent, but what it does is that it somewhat split the contribution of this term and this term, okay? And the way it does is that this term contributes a gradient, and this term essentially contributes a projection. And the algorithm is something like a projected gradient. You take gradient steps, but instead of just letting it be, you do some kind of a projection at each step, okay? So here's how it looks like. Suppose that this is the identity. Okay? Then this is exactly the gradient of the least square error. So if you put the identity here, this is exactly gradient descent. And the fact that you are regularizing would not appear at all. Okay? It would just be as if you were just fitting the data. Is that right? You see this? Yes? if you're actually regularizing with the L1 term, this contributes this stuff here, which is what is called the soft thresholding operator. In words, what it does is an operator that acts component-wise, first component, second component, third component, so on and so forth. And what it does is basically the following. If the component is small, but with respect to a quantity that depends on the regression parameter, I set it exactly equal to 0. If it's big, if it's bigger than a quantity dependent on the regression parameter, I don't just keep it as is, but I decrease it a little bit. Or even if it's smaller than a quantity that depends on the regression parameter, so in absolute value is big, I also don't let it be. I shrink them a bit to 0. This last step is annoying, and it doesn't have a modeling reason, it's a computational reason. So roughly speaking, the thresholding operator, in simpler terms, sets some coefficients equal to 0 if they're smaller than a threshold that depends on the regression parameter, or otherwise, roughly speaking, let them stay as they are. But I didn't write it. Yes, I wrote it. So, but this is not particularly enlightening, I guess. There are ways to write it, which is like less stupid, but or slightly less smart, I guess. So suppose here alpha is a parameter, okay? If you look before, is lambda gamma. We're going to check in a second what it is. But basically what this operator, so this is a component-wise operator now. If you give a number, it's going to check if the absolute value of this is bigger than a threshold, which means that it's either bigger than alpha or smaller than minus alpha. If that's the case, what I do is that I keep the same number, but I decrease it or increase it a bit. Okay? This fact that you don't keep it exactly as it is for computational reason. It's essentially to have a smoother approximation of a non-convex function. Let's just leave it as a detail. Okay? The important thing here is you check how big is this number with respect to this one here, and if it's small, you set it exactly equal to 0. This is the positive part of the number. So if this is smaller than this is negative, and you set it equal to 0. Okay? If you check what's here, it's lambda gamma. Okay? But roughly speaking, gamma is just a step size. You will see in a second that you fix it a priori. So in some sense, what you put equal to 0 or don't put equal to 0 only depends on the regression parameter. If the regression parameter is big, you put this interval is large, and so almost everything will fall within, and you're going to put a lot of coefficients equal to 0. If the regression parameter is small, this interval becomes very small, and almost nothing gets in there. Which gets back to the, the variational formulation. That's what you expect from here, right? If lambda is big, you expect to have a lot of coefficient different from equal to 0. If lambda is small, you're ignoring sparsity, so almost everything should be equal to whatever. I got lost, but you got it. Okay? And what you see is what I promised you, that at some point in this algorithm, you not only compute stuff, but you actually set it exactly equal to 0. While solving the linear system in regularized least squares with square norm, you're just estimating a vector, which can be small but never 0. Here, you exactly put it equal to 0. And the parameter that controls the whole business is the regression parameter. So that goes back to the question before. Okay? So, fine. A very good question one should ask every time is, how many free parameters I have? Whenever somebody shows you an algorithm, if it doesn't tell you all the parameters, a way to choose all the parameters is not an algorithm, it's a half algorithm. So it's always good to ask how many parameters you have and how you fix them. Okay? So here you have how many? How many parameters you have to fix? Come on, let's get out of here. How many parameters? Upper rows. Entertain me. Is X, this gets to embarrassing thing. Is X a parameter you have to, is Y? How many parameters you have to fix? Lambda, gamma, there's no epsilon. But yes, you have to estimate, let's say, how many iterations you have to do, okay? Here is what I call Tmax. So the good news is that if you pick gamma this way, where this is the biggest eigenvalue of the unnormalized covariance matrix, okay, of this x transpose x, this algorithm will converge to the solution of the previous problem, okay? So this is good enough. So you still have to compute this number. So you have to get this maximum eigenvalue, which costs you, okay? But you're good. When do you have to, how many iterations do you have to do? Enough. So enough here is, well, you have to choose some notion of some convergence criterion, essentially, okay? You can check two subsequent solutions and see when the difference become negligible, or you can choose when the thing doesn't change for enough steps. It's a heuristic, okay? And that's one of the problems. In practice, you put, for example, you could do something like this. You put a small threshold and you keep it going, okay? If you get that wrong, you might get a bit far away from the original solution to this problem, okay? So you should, in principle here, you want to do as many computations as possible. So the computational complexity of this, in principle, is infinite, because you have to do infinitely many steps. In practice, what you do is that you just take up to m step, and then the cost of this is not horrible. It's basically the price of making these multiplications, okay? And as I said, we already said this because this was the main answer to the question before. The main difference is that this gets you exactly 0 by trading off fitting or regularization, whereas Tikhonov does not. Now, it turns out that basically the same assumption that allows you to say something about matching pursuit work here. So if the solution is sparse and the data matrix is somewhat locally invertible, or in other words, doesn't have important columns which are too correlated, you can show that this will actually be as good as if you would have put the L0 norm as a regularizer, okay? So in this restricted class of subproblems, you can solve in polynomial time a potentially NP-hard problem. Now, let's see if I can convince you just with words. So we said that to prove that this works, columns, the important ones at least, should not be too collinear. They should not be too similar, okay? Because otherwise I have to confuse stuff. But suppose they are not the same, but they're very, very, very close. You can think that numerically what might happen is that the algorithm is going to jump from one variable A to variable B, B, A, and some combination, okay? So it's going to have some notion of instability. Because I'm actually shooting for picking just one, okay? I'm shooting for getting an exact sparse solution. So if I'm in close to the degenerate situation, I might have some notion of instability. Tikhonov, on the other hand, doesn't want to get to exactly 0, and if you put two small numbers, would be happy. So it's very stable. It doesn't solve sparsity, but it's very stable to these kind of situations. And so in some sense, in practice, I never used L1, but typically use what is sometimes called an elastic net for reasons which are obscure, but everybody calls it like that. And people here also like to call it an L1 plus L2 for kind of obvious reason, where basically what you say is, I kind of like sparsity because it gives me variable selection, but I also kind of like the stability in Tikhonov. So can I use both? Now, if you take a convex combination of the two, okay? And now you have two parameters. Lambda, you should really think of this as a regularization parameter, okay? And alpha. Alpha here is more of a parameter that is related to how much collinear things are. If things are perfectly collinear, you have to choose what you want to do. You can either try to shoot for sparsity, and then you're going to pick either one of them, or you can just say, give them both, okay? As soon as you put this term, notice that from a mathematical perspective, this is convex, but this is strictly convex, okay? So not only it goes up like this, but it induces a sharp minimum, which is unique. So it means that as soon as you put some of this, in the case where you have multiple solutions, you're going to choose one and only one. And now suppose the two columns are identical, so that you can choose any combination. Which solution you think is going to pick? In other words, you have two coordinates. You have to assign weights. And by choosing this, you will pick one specific way to assign weights to them. You can use a symmetry argument if you want to say that there's only one way to do this in a unique way. What is it? Equal weights. Okay? I have variable 1, variable 2. In the extreme case, I'm saying that they are the same. And I put weight here, say 2, and weight here 2. Because as soon as I do 4 and 2, I could exchange them and I get 2. Okay? So this will basically pick just the solution which shares the weight among all correlated, or in practice, closely correlated variables. Okay? So one thing, okay, and here you can use this to get something a bit more structured than just a list. You could try, for example, to get a minimal list and then try to increase it by adding correlated variables. And this, in principle, should not change the prediction. You're just writing the same solution in two different ways. One way, you just pick one variable. And another way, you pick another variable which is correlated to the first. Okay? But this is more of a heuristic. The algorithm to solve this is pretty much the same as the one you've already seen. There are minor modifications, okay? Essentially, alpha appears in a couple of places, and it also appears in the step size. So the parameters now are 3 because there is alpha, and alpha is a parameter where basically you say how much you want to kill sparsity in favor of smoothness, or if you want, stability. One good news from a computational perspective is that by adding this term, we make problem not only strictly, but actually strongly convex. Now, essentially, when you have a convex function, what is hard is that you know that it goes up, okay? But you don't know how flat it stays. And if it gets very flat, you might take a lot of time to get to the minimum, because you go down fast, and then you just keep on staying there, okay? Is in some sense a notion of condition number. It's a hard problem because it gets very close to be degenerate, okay? Or even it might actually be degenerate if it's just convex. It might be flat, okay? And then you have to decide where you want to stop there. If you add this term, which is essentially a parabola, you're actually avoiding this situation. And you're making the problem not only strictly, but actually strongly convex. It basically means that it goes up as a parabola. You can put a parabola below your function. This is important because what you see is that these are what is called the first order method. It's an iterative method that looks at the gradient information. And essentially one check that you can show that these methods have a much faster convergence rate the moment you make this kind of strongly convex perturbation. It's like what you might see it as from a numerical point of view as some kind of numerical preconditioning. Okay? So in some sense, I'm trying to sell you a bit the fact that while you have an extra problem of have to fix alpha, you gain both in some sense in terms of stability and in terms of faster computations to solve this problem. In the case where essentially the original problem is harder because you do have strong correlations among the variables. Okay? Oh. I fall asleep. So this is the last bit of the sparsity lectures. Okay, so this morning is actually a morning where you see a lot of stuff which is very different, and you cover quite a lot of material. Again, the first part, you try to reduce the dimensionality in an unsupervised way. You could also do it easily in a supervised way, but you don't care that much about picking up the important columns. You just want to look at some subspace, okay, which is spanned by a subset of my columns. And then you want to go from linear to potentially non-linear dependence among the variables. In the second part, you raise the bar and you actually ask if you can select the columns. And it turns out that the problem is in principle doable statistically, but hard from a computational point of view. And then you describe two potential techniques to actually do this. One is whose derivation is completely elementary, greedy methods and matching pursuit. The other one whose derivation has at some point the necessity of dealing with the non-convexity, the non-differentiability. And the good news is that the algorithm is still simple, but its derivation is not complicated, but we'd have to, it takes half an hour, say. Okay? So, what's next? Okay? In the PCA business, people have been trying to add constraints, where you say, not only I want to find eigenvectors, but for example, I want to find sparse eigenvectors. Because one question you could ask is, can you do sparsity in a supervised way? Okay, there are a bunch of ways of doing it. One way is, I want to do PCA, but I want to find eigenvectors that are sparse. So that I can look at then, so for example, I have the first principal component is actually sparse and it only depends on the first component. This means that the first column is the first principal component. Or I could say, well, no, the first principal components I can write in terms of the first and the second original column. Okay, this would be an equivalent version of PCA where not an equivalent, an extension of PCA where you add sparsity constraints. So one direction is to go this, so to enrich PCA by adding more constraint than just having the one norm equal to 1. Okay? And we mentioned already the kernel extension, and the kernel extension has a whole connection I mentioned to somebody during the break with what is called manifold learning. There is a whole interpretation that you can imagine, basically, instead of just looking at linear subspaces, when you start to look at kernels, you look at stuff which is nonlinear. And the simplest way to explain nonlinear things living in a linear world is to talk about manifolds, okay, which are locally linear stuff. And so there is a whole connection between kernel PCA, manifold, and manifold learning. And you can even look at manifolds as the place visited by a dynamical system, and then it would also give you a connection between manifold learning, kernel PCA, and the study of dynamical systems. As far for this part, so this actually, there was a huge amount of variation over this theme. From a modeling perspective, what people start to say is there starts to be really an industry of ways of building regularizer beyond this guy, or the sum of the two. For example, you could say, suppose that I have a process, biological process, where I do these measurements, and I know that there is a group of measure that is involved in a sub-process, and another group of gene which is involved in another sub-process. I know this sub-process, so I know the groups. And I don't want to select genes. I want to know how the sub-processes contribute to prediction. So I have gene 1, 2, 3, 4, 5, and then 6, 7, 8, 9, and then keep on going. And I don't want to select individual genes. I want to select groups of genes. Is there a way to extend this to cope with this situation? Yes. How about if my groups have a tree structure inside? Or how about they are just overlapping, okay? And I don't know anything about that. Can I still use this kind of stuff? What happens from a modeling perspective? I would hope that now sparsity is not in terms of individual variables, but is in terms of group of variables, or nodes of a graph that describe the groups, okay? Well, there's a whole set of work along this line that are basically called structure sparsity, okay? Where instead of just sparsity, you enrich the kind of regularization you consider. So, somewhat as a consequence of this, the kind of techniques of which I just show you an instance here with this so-called iterative structure shielding, this kind of stuff here, was actually the tip of the iceberg of a class of methods that are being considered. The good thing about this is that it's very, very simple, okay? And basically, it turns out that this is just an example of a much wider class of methods that are called forward-backward splitting methods or proximal methods. And basically, it somewhat emerged as the ideal way to solve this kind of sparsity problems, where the general rule is I'm going to design a penalty that tries to reflect my prior. Okay, here the prior was sparsity or just smoothness, Here, I'm going to try to design it on the basis of the prior information I have. And then as long as this term is convex, potentially not differentiable, then essentially you can use stuff that looks like this, where this term pretty much stays the same, but this term might not be just this softer shading I showed you before. Okay? This depends on the fact that I use the L1 norm. If I use some other convex norm, I don't have that anymore. I have some kind of projection-like operation. Okay? So roughly speaking, in the sparsity, one direction of extension has been, let's keep on looking at estimating vector. Let's try to look at much more complicated and rich sets of regularization and optimization techniques, first-order methods to solve it. Okay? Another direction has been, instead of vectors, let's look at more higher-order objects, say matrices. So for example, I say, I have a matrix. I call it W. W is not a vector anymore. It's actually a matrix. Okay? And then I have a matrix X, and now I have my output, which is not a vector anymore, it's a matrix. Okay? So you have X, W, Y, but this is not D by 1, it's D by T. So that this is N by T. And then the question here is, you may imagine a situation where essentially you're provided only partial information, you provide noisy information, you want to retrieve the original object. And then you can think of assumptions such as sparsity, but it turns out that these kind of techniques also hold if you essentially define norms over matrices. Okay? And there is an equivalent of the L2 norm of the matrices and an equivalent of L1 norm of the matrices, which is basically what is called the, one version of it is called the trace norm. Okay? So now I'm just shooting words there, but the take-home message here is, if you keep two vectors, you can generalize to more general regularization and optimization techniques to solve it. You can actually go to more complex objects than vectors, and in some sense, you still have a similar game where you have the L2 norm and then more, say, sparser notional. So you have more general non-convex regularization. Okay, and a lot of the reasoning here extend. And in fact, people also are trying to go beyond matrices to tensors and things like that, but tensors are nasty. So we're not at that stage yet. Okay? So this is kind of a big overview of what's going on. And as I said here, this last class especially is like the tip of the iceberg of a ginormous amount of work that has been done in the last few years. So it's by no means a proper introduction to the field, as it was, as Tuesday was just a nugget. All right? Okay. Any questions, or you're free for lunch? Questions? As Nicolas said, one question. Oh, okay. You can take it offline.